Exercise 1. Find the volume of the solid formed by revolving the region bounded by y equals the square root of x. Okay. And the x-axis on the interval from 0 to pi about the x-axis. So this about the x-axis, this tells us what our axis of revolution is. Two most common ones, as you can probably imagine, are the x-axis and the y-axis, but they can sometimes throw in an axis that outside of the shape someplace. It's always an external axis, not one that is internal to the shape, because whenever you revolve it around it would kind of overlap itself. It'd be totally confusing. So it's either on an edge or it's on the outside of the shape someplace. Okay, so this is probably one. So speaking of a shape, that you don't know what that shape is. I don't think at any point pre-calculus or algebra 2 that you graphed this thing as a parent function. You had to do SRT transformations, which means you probably need to throw this thing into the graphing calculator and get a shape that looks sort of like half a semi-ellipse, sort of. Okay, all right. And then our technique here is to draw in ourselves a representative rectangle, right? And we're going to take that rectangle and we're going to revolve it. Notice that it is vertical. It's vertical because it'll be perpendicular to our horizontal axis of revolution here. When I revolve that thing around, it's going to make a cylinder, which I can find the volume of. And for this particular case, what I'm going to do is I'm going to sketch a little picture to go along with this one. And then for this one, and probably this one only, turn it into a Riemann sum, which I will take the limit of, and then go from there, taking the limit. Did I say that twice? Probably. Anyway, definite integral. It'll look sort of like this. So here, let me get my white crayon. Yeah, there we go. And then I'm going to get rid of all of this writing here so I have enough room to make my disc. All right, what color is this? It's kind of like this yellow color. I don't know if I have. Okay, we'll use mustard. Okay, so I'm going to take this edge that's right here, kind of reflect it down over here to make my disc. Finish off my disc. It was 1. Well, that was very convenient. Okay, so let me connect these edges. Sort of like that. All right, and then maybe you have one that's dashed in the background if that doesn't get too busy. All right, and I need basically 2 pieces of information. My information is a height, which is going to be our delta x, and then we need a radius length. And the radius length is just the distance from the x-axis up to our function, which is this square root of the sine of x, right? So that is, I'm still writing in mustard. It's beautiful. Okay. Does it make you hungry for a hot dog, soy dog? Yeah, probably it doesn't. So let's set this up as finding some sort of volume of one of these disks, specifically just that mustard colored one that's right there. So it would be pi times my radius, and my radius is going to be the square root of sine of x sub I. So that's like a random x coordinate within this subinterval, left endpoint, right endpoint, midpoint, whatever, which we need to square. And then multiply that times our height, and then our height is the width of this disk that's right here, delta x. So there's the volume of one of them. If I were to take the summation from I is equal to 1 to n, now I have an approximation of this area using, or this volume using n of these rectangles, or disks, I should say. And then I would take the limit as n approaches infinity, and I'm taking a limit of a Riemann sum. Here's a function, multiply times a width, so it's definitely a Riemann sum by definition. That is a definite integral. This is why this whole thing works, that we can still take a volume instead of just an area. So I will pull this pi out of this thing, definite integral, and this delta x, of course, would have this whole b minus a over n thing, and this b minus a, that's our pi, and our 0, that's right there. 0 to pi. Oh, look at this. This is good. This double pi action. Anyway, and then when I square this guy, this is very convenient. These things are going to cancel each other out, giving me just, whoops, sine of x, no x sub I anymore, and then this delta x will go to dx. Easy. Why is it so easy? It's so easy because the antiderivative of sine is negative cosine. And then we'll evaluate that from 0 to pi. And then you know what? I'm just going to take this negative sign, just bring that on the outside with that pi, and then evaluate it using FTC. I've heard a number of questions asking me, hey, is this safe stoppable at this point? What do you think? Is all of the calculus done? No, it isn't, because we haven't done the fundamental theorem of calculus. Once you throw it in here, cosine of pi minus the cosine of 0, then absolutely it is done. Yeah, anyway, it's safe stoppable at this point, but I think that we can handle a little bit of trigonometry. Let's see. I guess I can use that same exact color. Here's my unit circle. And then we're at these 2 points. So over here we got a -1 for sine. Over here, of course, we have a 1, the x-coordinate. We've got negative pi times -1 minus 1. Inside I get a -2, multiply it times the negative pi on the outside, get a 2 pi units cubed. And so there is the volume of that solid of revolution. So were you able to visualize basically what this thing looks like? Let me give you a nice sketch of that thing. What does that look like to you? You might, if you're sports minded, think of a football, but I'm chocolate minded, so I usually think of those, those really nice Easter candies, that chocolate candies are wrapped in foil that are, they're delicious. If we were in class right now, I'd pass them out to you, but you just have to hypothetically consume one of these things.